Good morning, everybody. Welcome to day 5 of Organometallics. Last time we left off with a discussion of ligand substitution and the prevailing mechanisms of ligand substitution, namely associative and dissociative pathways. We compared the respective rate profiles typically associated with those mechanisms and discussed briefly how those experimentally determined rate laws can be used to distinguish between these two possibilities. As we mentioned, there's a rough parallel here to SN1 and SN2 reactions in organic synthesis, although I will admit that that's not a perfect one-to-one analogy. We'll continue marching along, wrapping up discussion of ligand exchange and then into the constructive bond breaking and bond making steps that will ultimately comprise catalytic cycles. Were there any questions from where we left off last time? Okay, picking things up. We'll discuss some specific cases. And so the first example that we'll consider is the ligand exchange of metal carbonyl complexes, particularly zero-valent metal carbonyl complexes, as exemplified by this molybdenum hexacarbonyl. Empirically, it's been observed that in these types of complexes, when one attempts a ligand exchange with phosphines, you typically will not get exhaustive ligand exchange. And the reason is that as you start substituting CO ligands, which are strong pi acceptors, as we covered, with phosphines, phosphines are now in general stronger sigma donors. That starts making the metal center more electron rich. That increases the bonding strength to each remaining CO ligand because the extent of back bonding goes up. That starts to have more and more double bond character, and the CO ligands become more and more tightly held. So let's consider this experiment where L is a representative phosphine. The particular phosphine is not so important here. We're going to treat molybdenum hexacarbonyl with a large excess of said phosphine. Let's make it trimethylphosphine for the sake of simplicity. And then one can imagine two different products being formed here. These are stereoisomers, or more precisely, diastereomers, because they are not related by mirror symmetry. If you look at these two isomers, they have a different form of isomerism than we typically encounter in the main group. We describe this arrangement as facial, where all three incoming phosphines are on one face of the octahedron, and the other isomer as meridional, or FAC and MER for short. Would anyone like to hazard a guess as to which would be the preferred isomer formed? Amy, you're whispering. Amy votes for FAC, and why do you make that vote?
It's because CO ligands are good that called? Like I can't remember what it's called, but it's like they like force ligand exchange opposite to where they
Are good,
um,
something influencing ligands. Trans influencing or transfect ligands.
Yeah.
So what does that mean?
It means that they like generally ligands will exchange opposite like trans to where the CO ligand is because it's a good trans-affecting ligand.
Aha, perfect. Well, that's a perfect segue then into what we'll cover momentarily. Are there any questions on that? So some ligands, and the point of covering this particular example is to introduce the concept of isomerism as it pertains to coordination complexes and this phenomenon of two different ligand exchange pathways being inequivalent. Okay, very good, Amy. So that will set the stage for something we'll cover momentarily, but first, a small diversion. And that small diversion is to discuss ways to encourage ligand exchange. And so this is preparatively often important. You, in organometallic chemistry, you want to drive formation of one particular product to test as a pre-catalyst or something of the sort. So we'll cover some common techniques. One tried and true technique is to treat a corresponding metal halide with a silver salt. And so what does that do? Well, a lot of ligand exchange events are intrinsically reversible, but we can drive this reaction to the right through Le Chatelier's principle because most silver halide salts are completely insoluble in organic solvents. So if we consider a specific example of, let's say, silver triflate, why silver triflate? Because silver is triflate is a weakly coordinating anion. Then that generates the metal triflate salt, and then normally metal salt here is the triflate counteranion is outer sphere. And even though if you could imagine, do this thought experiment and the silver chloride were to stay in solution, then this might not be thermodynamically favored because it's falling out of solution, it can be pulled to the right. Okay, along these lines, and this was proposed as a plausible mechanism in the context of one of the reactions we covered in an earlier class with ferrocene. So metal hydride salts, if you want to remove the hydride, one common strategy is to treat with a proton source. And we'll talk about metal hydrides at length and their different character in terms of being protic or hydridic in character. But for hydridic metal hydrides, they can be protonated off. That generates H2. Again, similar to the previous case, because now you have loss of H2, presumably into the headspace of the reaction vessel or something like that. You drive what could be a reversible reaction far to the right. We just covered an example of metal carbonyl substitution, ligand substitution with metal carbonyls. And sometimes this can be recalcitrant. It can have a high kinetic barrier for this ligand exchange. And so a common strategy is to irradiate with light. That will drive off a CO ligand so that said CO ligand is now replaced with solvent. Let's say it's a coordinating solvent like THF, and that can then lower the barrier for a subsequent ligand exchange. Does anyone want to hazard a guess as to what irradiation with light could be doing in this type of metal carbonyl complex? Amy, you had a
you just
reaction.
take off it, like it just dissociates CO.
Yeah, it's a photo-induced ligand dissociation, but let's get into the electronic or orbital considerations for what might be happening there. So why in general are metal complexes light absorbing?
It's because they have empty orbitals, and there's like places for electrons to go.
Perfect. You have a transition whose energy, an electronic transition whose energy is commensurate with the energy of incident light. You have a filled, typically metal-centered orbital, not always, but metal-centered orbital. Let's call it a d electron, an electron with predominantly metal-based d orbital character, and then you have some antibonding orbital. Let's call it a pi star antibonding orbital or sigma star antibonding orbital. We can think through which of those would be lower energy, but you are exciting from filled orbital to empty orbital, and that in turn then destabilizes the bonding interaction. And remember, the metal carbonyls are not chelated, so when you destabilize these bonding interactions, that can be enough to drive off one of the ligands in exchange for solvent. Sam, you had your hand up. Do you want to add anything?
I was thinking about the dimer of like cobalt or manganese metal carbonyl can be photolyzed with like near UV to make metal metalloradical.
Great, that's a great connection. So metal carbonyl dimers, like I think the one you invoked is cobalt carbonyl, upon irradiation can dissociate to generate the corresponding metalloradicals. Similar kind of principle here. You are exciting from predominantly, from the metal-based d orbital to some typically ligand-based antibonding orbital, and then that destabilizes the complex and causes it to fall apart. I think some of the dynamics at play there are still under some investigation, but it's a simplified argument. Okay, and then some of these examples we covered to an extent in the main group lecture. So other methods for ligand exchange. So let's say we have a metal halide, or this is you can imagine in a Kumata coupling, you have a nickel halide, a palladium halide that's on the catalytic cycle, and this can undergo transmetallation with an incoming Grignard reagent. The Grignard, the driving force here is formation of this very stable magnesium salt. And then likewise, that exact same conceptual framework can also be used to transmetallate on hydride ligands with also corresponding aluminum salt, boron salt, silane salt, silicon salt, etc. Okay, any questions on that? We'll jump in to finish our last problem of the day, lingering problem of the day from the day 4 notes. I'll try to share that PDF quickly. Having some problems with my computer, so you might have to bear with me as I try to navigate the screen share. My computer has decided it doesn't like opening files anymore, so that makes it challenging to use on many fronts. Okay. So problem three from last time's day 4 handout. We're encountering here a strange looking ligand, a germaline, but we've tried to draw this in a suggestive way with this lone pair on the germaline to give you a hint about how it's going to coordinate. We're going to react this at room temperature in coordinating solvent with tungsten 0 tetracarbonyl cod complex, and then we will form a new complex W1. The hint here is that the C13 spectrum of 2 contains 4 inequivalent peaks in the carbonyl range. So take a minute to propose a plausible structure for W1, and I think it's fair to say there might be more than one right answer here. You can then, based on what you've, so if you have more than one idea in your mind, please list more than one idea. Then jot down the coordination number, oxidation state, the electron count, overall electron count. Then think through in terms of what we've covered, what the mechanism for ligand exchange might be, and then what you would expect might be more likely. All right, Hermione Rand, give me some thoughts on your reasoning here. You're still thinking it through, then just whatever's on your mind.
Thinking because of the lone pair, it should be a L-type ligand.
Okay,
Okay, I wanna switch your screen.
yeah. All right, so the germaline, you're thinking that looks vaguely like a carbene or something like that. So let's call that a neutral donor. It's going to form a dative bond. What else are you thinking about? How are you thinking about that sulfoxide? All right, Clara, what do you think for the sulfoxide? How would you treat this?
So I guess you're getting at that it can also be a ligand in this case.
I am not getting at anything. What do you think?
I originally didn't think that, but I guess it could be.
Okay. So we're thinking germaline could be a ligand. And if that were to happen, then let's say it's germaline only, then we would probably displace one of the olefins of cod. And then we would have a germaline, in this case, so this would be one solution. And the other one would be cod. And this would maybe fulfill the specifications of the question that all the COs are inequivalent, yes or no? Well, we said in the C13, we see 4 COs. So that means they're all in different electronic environments. It could be, they could be inequivalent, but there is potentially a mirror plane. It kind of sort of depends how quickly the germanium is rotating, but I think if you drew this, that is not unreasonable. to consider. But what if I give you the hint that a sulfoxide, even though it's not a super strong ligand, is a common hemilabile ligand for a metal?
So the con would just be
Okay. So we'll then draw this. And what do you like? Do you like through sulfur or through oxygen? Through oxygen. Okay. Why do you like through oxygen?
because it has like no lone pairs.
Okay, but the sulfur has a lone pair too.
Maybe because it's just better coordinating then.
But is it better coordinating than sulfur?
Maybe because sulfur has like more bonds than oxygen right now.
Okay, so this is, and did anybody who was thinking chelation, did anybody else like through sulfur? Maybe show of hands. A few people like through sulfur. Oh, okay, getting interesting. Ningxi, you like through sulfur. Why do you like through sulfur?
Sulfur is just softer, so maybe it can coordinate better with this low valent tungsten.
Okay,
Tungsten 0, right?
I like this soft, hard thinking. Anybody who picked sulfur have anything to add to that? So the coordination chemistry of sulfoxides is indeed complex. So they're hemilabile ligands. They can coordinate through sulfur or through oxygen. So again, based on the information you're provided, either would be reasonable to draw. Typically with first row metals, there's a tendency to coordinate through oxygen. And with second and third row metals, it can be either, but there's more of a tendency to coordinate through sulfur. Hard, soft, acid, base theory is one reasonable explanation. Now, if you had to, I didn't ask this, but since we've gone down this direction, I'll ask you to think through, how would you disambiguate? Obvious one would be X-ray crystallography. That would give you a readout in the solid state. But if you didn't have X-ray crystallography, or you wanted to understand the solution state structure, Oliver is going to tell us how he'd go about it.
I was actually going to ask a question.
Oh, okay. He's going to ask a question.
Does it depend on the steric bulk on sulfur, if it goes to the sulfur versus the oxygen?
That can be another factor for, but in this case, well, maybe I won't give it away yet. But I think even with pretty bulky groups on sulfur, because sulfur is large and diffuse, it can still form stable bond interactions, even when that's a tert alkyl substituent. Okay, any thoughts? So X-ray is one, that's obvious. And then if you didn't have X-ray, I think she's either stretching or he's gonna.
Can you do carbon sulfur correlation on NMR?
Carbon sulfur correlation.
So between the carbonyl and the sulfur.
The carbonyl and the sulfur. What, I see. Maybe you would need some controls. You need some standards probably. Yeah, Riku,
Look at the SO
how?
bond length or
IR, okay. Bond length, again, you would need an X-ray, but, and if you, then if you have X-ray, you will know the connectivity, so you won't need the, so Riku's onto something here. The idea is that you could use, IR here as a so here you want to compare free sulfoxide versus the bound forms. And what we're really talking about here is these two resonance states of, so this has nothing to do at this point with coordination chemistry, but you know that sulfoxides have these two predominant resonance forms, and there's been a lot of physical organic work and computational work. The ground state bond order is typically thought to be closer to 2. That's why we draw it this way. But then you can quickly appreciate that which of these 2 resonance forms is the dominant player will directly be tied to IR. So when it's S-bound, you're favoring this coordination form, or this resonance form, sorry. And that, I think, intuitively makes sense. When you have more anionic character, it's going to be a better ligand. And when it's S-bound, you're favoring this coordination. And I think I don't have the exact numbers jotted down, but when it's S-bound, you're typically seeing close to 950 wave numbers. And when it's O-bound, you're typically seeing something like 1100 wave numbers. And if you are really into this, maybe some people like in Jin's lab, sulfoxide is a nice ligand for palladium. Of course, you can introduce stereochemistry at sulfur as well. If you're into this, then I'd direct you to this chem rev. So we can take a IR and read out which of the versions it is, or get the X-ray, and this we'll find out. This is the form in the solid state, at least, and I think also the form likely in solution state. Couple questions. We'll do Riku first.
I think she was talking about the soft hard.
Yeah.
So I understand why the sulfur lone pair is soft, but so why is the tungsten centers?
Yeah, this is a good question. In this case, it's tungsten 0, so it is pretty electron rich. It's an early-ish transition metal, so you might not be immediately clear in its second row, so it's kind of a potentially borderline case. That's why we would probably want to run the experiment, because we wouldn't know a priori. But 0-valent metals in general are softer. Julian.
When the sulfoxide is O-bound in the O- form,
Yeah.
do we consider it as an X type of ligand if it's ionic, or
Well,
how do we treat it in terms of
yeah,
X and L type?
we'd still just call it an L-type ligand. So in either of these cases, we're going to call it an L2 ligand. Because if you did the treatment and you called it an X-type ligand, then you would have to call it an X-type ligand that's also +1
The other side.
the other side, and then this will all break down to, all reduce down to the same as if you just treated this an L-type ligand from the start.
Yeah, but it doesn't actually remove any electrons from the metal when
Right.
it's bound.
Correct.
Thank you.
Any questions on that? Okay, and then so that's great discussion. Part B of this was, what is the likely mechanism? Oh, sorry, the electron counting. So maybe I'll go back to Hermione. If we assume this version now, then give me an electron count.
I do the neutral method, so I will count tungsten as 6 electron. And
Coordination number 6, and you said tungsten is, you said tungsten 0, so it's D what?
so it's
D6.
each carbon though I count it as 2.
6 L-type ligands. 12 electrons. So overall is going to be 18 electrons. Okay, so with that in mind, then what ligand exchange mechanism do you think is more likely? An associative mechanism requires the ability to coordinate a new ligand to go to a higher electron count, overall electron count.
So since it started with an 18 electron complex wall, so I think this associated would be more likely.
Brilliant. We don't have any data here, so we just go on based on what we have, and if it 18 electron makes dissociative more likely, and then we'd be saying, okay, are there any tricks here it could do that would make it be able to undergo associative, like a ring slip or something like that, but we don't see anything like that. So likely one of the arms of the cod has to fall off, open coordination site, ligand comes on, other arm of cod falls off, and then sulfoxide coordinating. Questions on that? All right, we'll move forward. Amy got us started on this, the trans effect / trans influence. So empirically, it has been observed over the years that different ligands are more or less effective at labelizing ligands trans themselves. So again, it goes back to this idea of isomerism, appreciating that not all metals with the same elemental composition are laid out in space the same way. And then how do you get access to different stereoisomers? And so it has been observed that different ligands have these different effects. There's two terms that in the literature are used not always consistently and sometimes confusingly. There's the trans effect, which is the kinetic descriptor, and trans influence, which is the thermodynamic descriptor. So let's think this through. Trans effect, we're thinking about rates. We're thinking about transition state energies. And on the other side, thermodynamics, we're thinking about things like bond lengths, as read out by X-ray crystallography, stabilities. And so these tend to move in the same direction, but they are not equivalent. So that's important to keep straight in your mind. So if you're doing a midterm and you say that this bond is shorter than this bond, and that's evidence of trans effect, that wouldn't be strictly accurate because that you'd be reading out trans influence. It is this idea of trans effect, trans influence is most important for D8 square planar metals that are proceeding through this type of associative ligand exchange. And here is the lay of the land. And I think Amy already set the stage really nicely. So the ligands that are best at labelizing ligands trans to them have, and you see that we have this case study of CO being a better trans effect ligand than phosphine. So there they are on this. This is an empirical trend, and it first pass looks kind of similar to the spectrochemical series, although it is not equivalent. Like the spectrochemical series, though, it has this this feature that the exact ordering of ligands depends on the metal that you use to collect the data. And so if you have learned something else that looks qualitatively similar but different in some specific cases, it's probably because you learned the trans effect based on a different metal. This one is based on platinum salt, straight out of the Crabtree textbook. So those ligands that are strong trans effect ligands are typically strong sigma donors and pi acceptors. And those on the other end of the spectrum are weaker sigma donors and often pi donors. And this pi accepting and sigma donating character is especially important. We'll talk about why that is. And in terms of a mental model, like a heuristic or a mnemonic device, it's not really a mnemonic device, but just a general first pass, one way you can think about this, and this is not technically accurate, but I think to me has always been useful in the back of my mind, is if you imagine that the metal, these two ligands, the trans influencing and the outgoing ligand are interacting, let's say, with the dx squared minus y squared orbital, they're interacting with the same orbital on the metal, then there's this sort of tug of war for bonding strength. And when the trans influencing ligand is forming a super tight bonding interaction and accepting electron density from the metal, that is weakening the opposite bond and causing that ligand to preferentially depart. Now, that is not strictly accurate, but I think as a first approximation to me, that's always been useful in the back of my mind. When you have this tug of war for electrons, one's bonding stronger, the other wants to go. So that's something that you can hopefully take away and use as a guide. If we zoom in on that, we'll see that it's a it is a oversimplification. So what's really going on here is, remember, we're proceeding through this associative ligand exchange mechanism. So we have the incoming ligand denoted here as Li in darker green here. This reacts through associative ligand exchange, and the metal will then adjust to a different coordination geometry, that of trigonal bipyramidal. Now, in a trigonal bipyramid, there's this interesting feature that along the equator, those positions have higher basicity. There's more electron density. And so ligands that have pi accepting character would prefer to be oriented around the equator. And then if you just play this out based on the principle of microscopic reversibility, the incoming ligand and the outgoing ligand, the incoming ligand and the incoming ligand and the outgoing ligand will be the other two that occupy that equatorial position along with the trans-influencing ligand. And then that will eventually collapse to dissociate the outgoing ligand. And then you can run this thought experiment and say, okay, well, if that's the case for a pi accepting ligand, then pi donating ligand is going to destabilize that exact same trigonal bipyramidal intermediate, and that would make that pathway disfavored. So I've drawn here just one possible trigonal bipyramidal intermediate that's generated, but you can play this out and draw the other ones for more weakly trans-influencing ligands. Okay, let's consider now a classical, historically important case. And this one, I think every organometallic class probably that is taught on planet Earth covers this same case study for trans effect. So what we're going to do here is treat this platinum tetrachloride salt with ammonia. So start thinking through what's going to happen here. The first one is self-evident, so I'm just going to draw this out. So we have a ligand exchange. We're going to exchange on one equivalent of ammonia. Nothing too complicated here. And now -1 charge. Okay, and now we're going to take this one step further, and we have two inequivalent ligand exchanges that can happen. So Pierre, what is going to happen here? For the trans, tell me what we're going to get out of this.
Well, the is fairly strong sigma charge, which makes for a strong trans effect, and thus the second displacement will occur in trans.
Trans to what?
Okay.
Trans to the amine. Okay, so let's just play this out. So in theory, we have what can leave? These are the three inequivalent ligands that can leave. If ammonia leaves, that's just degenerate, so that's we don't have to consider. So then we have two inequivalent chlorides that can leave. And what we need to do then is just scroll up and say, okay, so then we would define what are the potential trans-influencing ligands. So we've got to think about the relative trans-influence of a chloride and ammonia. So let's go to our chart. We see both of these are pretty weak on the trans-influencing continuum, but amines are even weaker than chlorides. So that says chloride is gonna win out in this battle. And this is the ligand that's going to be labelized. So let's draw that out now and are using the same color coding scheme as above. So the departing ligand is going to be this one. The incoming ligand is going to be this other type of green. And what we have out is what comes out of this. This, and now this is charge neutral, so we can delete this. Okay, and do you happen to know the name of this complex? David, got it.
Transplatin.
This one is cis, so the platin part is right. So this is cisplatin. And then the other one that David mentioned is transplatin. So just based on this framework, then, if we wanted to engage in a simplified retrosynthetic analysis that's guided by the trans influence, how would we get access to transplatin, where the two ammonia groups are opposite? Kevin.
Just start with the fully saturated ammonia. And then you can displace on 2 chlorides.
Love it. So Kevin's saying, take the platinum tetra ammonia 2+ complex and iteratively displace with chloride, taking care to stop after 2 displacements. And if you think through based on the trans influence, that will get you to transplatin. Brilliant. That brings us to our day 4 chemist of the day. Does anybody know this individual? Famous for research on this very topic. Sebastian, did you have your hand up? Or were you?
I did not. Sorry, I don't know.
All good. Any takers? Wenji? This is Steve Lippard of MIT, famous for foundational work in the field we now call bioinorganic chemistry, including the structural elucidation, functional and structural elucidation of cisplatin that functions through this interesting mechanism of coordinating to DNA and then inducing cross-linking of DNA. And so this is a predominant and still somewhat widely used anti-cancer agent. So it's not particularly selective, it just goes after the fastest multiplying cells, which tend to be cancer cells in a cancer-infected patient. And I just draw your attention to this really nice study from the Lippard group that has some beautiful coordination structures of cisplatin bound to DNA model systems. Couple questions. Yeah, we'll do Clara first.
Question about the above problem. How did we decide which chlorine would be removed? Last step.
So in the last step, there between green and pink, or between
The
green and not colored?
not colored,
Okay, well, green, let me see.
the one above it.
Oh, maybe did I mess this up? So this thing maybe meant that two of the 3 end up being equivalent is the short answer. And so if you displace the green versus the pink, the green and pink are equivalent. So they're influencing each other.
What is the one above the yellow? Yellow uncolored.
The uncolored is being trans-influenced by the ammonia.
Okay.
So there's a symmetry element in the starting complex. Pierre.
Instead of ammonia, you were using sodium amide. How would this play out?
That's an
That's what I had originally thought I had read. There.
interesting question. Well, you would then have to think that through before I hazarded a guess. It's different because you're, you have in this case, you have an anionic ligand. Yeah, off the top of my head, I am not sure. Do you have a hypothesis for what would happen? You would not get to the same products at least and before some kind of protonating work. Right. That's the first thing that would be different is you wouldn't make these products. Now, what the stereochemical consequences are. Now you're going to have to compare the relative trans influence of NH2 versus a chloride. And I don't have that on this sheet. I guess I might expect still the trend to hold, but I could be wrong. Was there one more question?
Sorry, how to make the transplant question, it's not very, it's not a kind of a stupid question, but you can make transplant from cisplatin by first like flooding with ammonia, then using chloride minus.
Yeah, you could.
Sorry, but that's like exactly this.
Yeah. Okay, we'll march forward then and can cover another empirical trend. This one is of particular importance now for octahedral metals. And this is the so-called cis effect, where some ligands have the tendency to labelize ligands that are cis with respect to them. So here's the empirical trend. And again, first approximation, you see that it's roughly opposite of the trans effect, but there are some interesting examples to consider here. Nitrate, acetate, formate, carboxylate, which is missing a minus charge. What do these have in common? We could draw these out.
They can be bidentate.
I think I heard that Alex whisper, they can be bidentate. So how would that be useful?
Because you can imagine as the departing ligand leaves, then, you know, the acetate, for example, can close down on the coordination site and hold that down basically until the incoming ligand comes and displaces that.
Perfect. So strong cis influencing ligands are bidentate or have the capacity for being bidentate. They're kind of the opposite trend of the trans influencing. And again, it comes down to this now common, somewhat common trigonal bipyramidal intermediate that is formed upon now like a dissociation. So you're an 18 electron complex, it's going to proceed through a dissociative mechanism. Upon dissociation, you will get a distorted octahedral geometry or trigonal bipyramidal geometry. And then we can apply the same principles that we learned for the trans influence with this added asterisk of bidentate coordination the capacity for bidentate coordination being stabilized. And we see this with carboxylates, nitrates, sulfoxides, as we just covered, have this ability to coordinate in two potential positions. So that's something to keep in mind. Okay, questions on that? All right, let's march forward. Problem of the day number 1 on the day 5 worksheet will give us a chance to practice some of what we have just covered. So we're going to consider here this tetracarbonyl manganese halide complex. And we have an incoming triphenyl arsenide ligand. So this you don't need to worry too much about. Just think of this as, in your mind, you can replace arsenic with phosphine and it behaves just like a triphenyl phosphine that is a little bit softer and has more diffuse orbitals. So predict the product or products if you think it might form multiple products. And then part B is to order the 3 complexes in terms of expected reaction rates: chloride versus bromide versus iodine. And your answer to B might depend on your answer to A. So maybe we can do A. So take 30 seconds to jot down your thoughts. All right, what do we think here, Oliver?
The iodine's more reactive. That would go first.
Okay, so let's do the product first. So what did you have as the product? Let's talk through what are all the possible ligand exchange events here. You could exchange the halide, you could exchange this CO, and note that this equatorial CO is equivalent to the other 3 COs or the axial CO. So which of those did you like dissociating? Maybe I'll draw it. Maybe I'll move this here. Okay, so what did you think here, Oliver? We can just play this out, and this might be a useful exercise. So let's first consider displacing the halide. We don't have to think about any underlying mechanism or anything. We're just going to play this out, all 3 possibilities. Okay. Is there anything you don't like about this possibility, Oliver? Anyone else? Kevin?
I think you're driving into a charge complex, which just seems less stable. So I think a CO would dissociate first over the halide.
Okay, so you don't like displacing the halide because you're trading a X-type ligand for an L-type ligand. You're getting a charged complex, which in and of itself is not a bad thing, but you have other possibilities of complexes you can make that are not charged. And so which of these did you like?
I think based on the trans effect, if I remember correctly, the CO is a stronger trans effect ligand, so the carbon monoxide opposite of another CO should leave, I think.
So you've got,
So I think your top right one looks more.
the top right one. Okay, so you like this one.
Yeah, but then it doesn't answer your second. It makes it so that part B seems weird that you're asking, so.
It makes it seem weird. Okay, well, so the trans influence for all three of those complexes will be the same. So what's the other influence that you could?
Well, yeah, so based on your question for B, then it means that your bottom one is the preferred complex and then the ranking should go.
Well, not necessarily, just saying that trans influence across that series is going to be more or less constant. So then you can differentiate with a different, yeah, Julian.
I was just gonna say, is carbonyl a stronger field ligand than the halides? So would we expect the halides? I know we're discussing maybe issues with the ionic species on the top left.
Yeah. Well, stronger field, yes, but that stronger field is referring to splitting energies. And so that's a different concept than trans effect.
Well, I just meant for the displacement, for the initial displacement.
Yeah.
Of the halide versus the carbonyl. Would the carbonyl be more tightly
I
bound
see.
to the metal center?
Yeah, the halide, so the halide, we can rule out that possibility, and I think you can think about that different ways. So one is as we said, that going to a charged species, particularly when you have very pi acidic CO ligands, is not going to be favorable.
Okay.
Alex?
If not trans influence or effect, then cis effect.
If not trans, then cis. I like that logic. And then what would you get?
So I would say, I mean, the halides are a better cis effect ligand than carbonyl, so you should substitute cis to the halide. And according to the order you gave us, chloride is the best, bromide's in the middle, iodide's the worst.
Okay.
So I expect the rate to parallel that.
Okay. All right, and we can, in fact, quantify that. And I just jotted this down here. Is this in line with your prediction, Alex?
Yes.
Iodide fastest, then bromide, then chloride, differentiated each by about an order of magnitude. All right, good. Any questions on that? Okay, quick point of terminology here. You will hear this in talks, you will see this in papers from time to time, nomenclature here of spectator ligand versus actor ligand, also sometimes referred to as ancillary or reactive, respectively. This is easiest to understand just by considering a specific example. The specific example is an alkyne trimerization, something we'll cover a little bit later. And so in this alkyne trimerization, you have a couple different things going on. You start with this pre-catalyst, a bisphosphine ligated ruthenium CP chloride. First thing that needs to happen is to open coordination sites for the reactive alkynes to coordinate, so that makes the phosphine ligands actors. The alkynes, of course, are reactive, so those are actors, and then the ligands that are doing nothing throughout the course of the reaction are not doing nothing. They're still influencing the steric and electronic profile at the metal center, but in a more indirect way, so they're referred to as ancillary ligands, the CP and the chloride. Okay, let's jump in now to oxidative addition, where things will really start to heat up here. So we'll cover oxidative addition and then its microscopic reverse process, reductive elimination. And reductive elimination we'll cover a little bit faster since it's essentially the opposite story of what we see here. And so oxidative addition, since we're generally organic chemists and we like arrow pushing, this is how we can think about that. Pushing electrons from a filled d orbital on the metal to the reactive organic substrate / ligand, however you want to define it, to break a sigma orbital. So you're donating electron density into the sigma star antibonding orbital to break the AB bond, and then the A will reassociate as the ligand. So you can see that in effect, we're trading 1 sigma bond for 2 sigma bonds, substrate sigma bond for 2 metal ligand sigma bonds. Because this step involves pushing electrons off the metal center must have d electrons. We talked about how in order to engage in pi back bonding, you need to have a d electron count greater than 0. And so by extension, to undergo oxidative addition, you need to have d electrons that are up for the game. And so you need d electrons for oxidative addition, just like you do for back bonding. Oxidative addition can just be viewed as an extreme of back bonding, where the back bonding is so pronounced that you actually break the bond in question. In order for the elementary step to happen, you need a vacant coordination site for the substrate to bind. And then if we think about how the electrons are flowing and what's happening just from this simplified picture, I think you can get an intuitive sense about what factors are going to favor this elementary step. Because electrons are flowing off the metal to the substrate, electron-rich metal center is going to make this process more facile, sterically unencumbered metal center, and then that directly informs what types of ancillary ligands, non-reactive ligands are going to facilitate this, those that donate a lot of electron density, those that are sterically unencumbered. So think here like trimethylphosphine is a very good ligand for promoting oxidative addition. What happens if we think about the electron counting consequences of oxidative addition, we see that the metal's oxidation state increases by 2. The coordination number of the metal center also increases. We'll see how that plays out. Because we've removed electrons have flowed off the metal to the substrate that then becomes ligands. We decrease the metal's d electron count, which is just another way to say that the oxidation state has increased. And then we talked about the ligands that promote this process. So now we'll go through and cover different substrate classes that can undergo oxidative addition. So in the Hertwig textbook, if you're following along, it's organized by substrate class, mechanism, substrate class, mechanism, substrate class, mechanism. Here it's organized by just these are the substrate classes, and then below we'll cover what the mechanisms are, and then you can think about how that plays out and what the crosstalk is. Okay, substrate classes. The first one is categorized as nonpolar. So this is an AB bond, not involving a highly electronegative atom. These are things that you look at and you say, these are not good oxidants. So if you want to apply your organic chemistry intuition, if you look at something and you say, that's not a strong electrophile, that's not a strong oxidant, then you're likely in this bin of nonpolar substrate classes. This includes things like H2. So we saw this example of H2 forming a sigma complex already in class. And then by extension, CH bonds, SIH bonds, SH, NH, CC bonds, SS bonds, etc. And then for the oxidative addition process to take place, you need an open orbital for the substrate to bind in the first place, and then you need an adjacent vacant orbital for this mechanism we're going to see, which is a concerted oxidative addition. And then the opposite category, if you want to think of it that way, or a different category, are those where the AB bond contains at least one highly electronegative atom. So think here, the ones that would immediately come to mind if you're thinking about cross-coupling reactions are things like organohalides. But by the same token, dihalides are good oxidants. We all know that. And so those fall in this bin. Things like mineral acids, HX. Sometimes these are, depending on the textbook you read or the slide deck you're following, these are considered their own category, but I think they share a lot of the common features of other polar groups. So I include them here. So think things like HI, HBr, HCl, et cetera. And then as we start to think about the mechanisms here, you'll note that in this case, you do not need this vacant orbital that we saw in the previous case, because what is going to happen mechanistically is it's going to be more like an SN2 process where you directly populate through a quasi SN2 process, this AB sigma star antibonding orbital, and you're only forming one new bond to the AB adduct. For 16 electron complexes, both A and B coordinate. They will often coordinate trans. We'll see that. And then when it's 18 electron metal starting material, typically only one will coordinate, and it's the ligand that is strongest binding. And then there's a category of AB reagents where the AB bond is retained, and so sometimes that's because the AB are actually multiply bonded. And so examples of that are O2, which upon oxidative addition, let's say O2 initially binds Sidon, and then you have an oxidative addition, then form this kind of adduct. And then we talked about metallocyclopropane. So if you coordinate an alkyne, you can make a metallocyclopropene and oxidatively add to that by the same law. And so some kind of bonding interaction between A and B is retained. We got a sneak preview to this idea of multi-metallic processes in the discussion of one of the previous problems of the day. And this starts to get quite complicated, so I won't go into this in too much depth, but I do want to highlight it to paint a picture for the class that this is an area of intense research in the modern organometallic literature. And so I've highlighted two general flavors of oxidative addition here, the homo bimetallic. So one of the leaders here is Chris Ueda, and there's an example highlighted from his group's lab from a few years back, where these naphthyridine complexes that are capable of supporting dinickel, dicobalt, diiron can undergo oxidative addition and then maintain metal-metal bonding interactions in the resulting product. There are also heterobimetallic, so cases where there's a metal-metal single bond or multiple bond that's non-symmetric, and then upon oxidative addition, you will form a bonding interaction at each of the metal sites. And so this is an example specifically from Neil Mankad's group in the context of a catalytic CH borylation, reminiscent of the ones you might typically see catalyzed by iridium, a nice base metal solution to a reaction typically promoted by precious metals.
Can I ask a question?
Yes.
I just don't know much about So what are like the general advantages that are offered from bimetallic?
Versus monometallic. For oxidative addition specifically, or in catalysis in general?
Would you be able to answer both?
Sure, so, yeah, so I think oxidative addition specifically, or kind of like for a given elementary step, you could think this through, like the advantage could be that you have a higher number of mechanistic pathways that you can find a low energy path through the potential energy surface. So for example, we just mentioned that there's this requirement for having an open coordination site after substrate binding if you want to undergo concerted oxidative addition. But if you have a bimetallic pathway, that open coordination site can be on the adjacent metal. So you can coordinate at one metal and then the other one can accept the carbogenic substituent from the AB, for example. So it can allow you to oxidatively add to functional groups that you might not easily be able to oxidatively add into. In the context of catalysis, I think one way to think about this is that if you just view it, if you localize yourself on one of the metals and you pretend you're M1 and you have your friend M2 next to you, then having a metal bonded to you gives you a lot of interesting possibilities, because that metal, that friend, can be a electron reservoir. It can take some of your electrons, it's like any friend in your personal life. They can carry some of your troubles when you're having a hard time, and when you're having a good time, then they're along for the ride. So they can accept electron density when you have too much, and they can give it back. The partner can give it back when you need it. And so they can have this electronic communication that allows you to be more electron rich or more electron poor at a given point on a catalytic cycle when needed, or at least that's the pitch. I think the full promise of this concept has not been fully realized, although it's very exciting. Amy is has a lot of experience in this area, so she can probably answer some of these questions offline better than I can from her experience in the David Michaelis lab. Okay, let's talk. Did that answer your question, Riku? Yes. Were there any other questions before we charge forward? All right. Let's talk now about mechanisms. We've already hinted a lot of this, so we're basically just going to formalize stuff we've already hinted at. We're going to cover 3 mechanisms: concerted, nucleophilic, which is also in the literature referred to as SN2 type. Actually, I think it's referred to more as SN2 type than it is nucleophilic, and then radical. We'll cover the different types of substrates that fall into these different bins, and the requirements and reactivity trends, et cetera. So common for the nonpolar substrates is this concerted pathway. It involves initial side-on coordination of that sigma bond that's going to be reacted, and then a 3-center 2-electron transition state. 2 electrons from the metal flowing into the sigma star antibonding orbital of the ligand. The reaction is stereospecific in the sense that it introduces the 2 ligands cissoid with respect to one another. Often there can be a subsequent process where those newly added cissoid ligands can reorganize to a trans orientation. So that's a caveat that you need to be careful of. If one of the AB groups is a carbogenic substituent, let's say, for example, it's an alkyl halide, and it's enantioenriched, then it will be stereoretentive at the carbogenic substituent. We mentioned above, it requires a coordinatively unsaturated metal for the substrate to bind, and then another open coordination site for the ligand that will be introduced. In terms of reactivity trends, we can consider, there's a nice paper, it's a computational paper, but it highlights the origins of these reactivity trends really nicely. And one of the things that you will, if you take a minute to think about this, one of the points that you might find initially counterintuitive, and I found initially counterintuitive. So let's take the case study of CH bonds. One of the things that is, so that's this case where X is H. And this also holds with alkyl halides as well, alkyl halides that are participating in this concerted mechanism, which is a caveat there. But let's consider the case of CH bonds. One of the things that at first you might be uncomfortable with is that the strongest CH bonds are those where the carbogenic substituent has high S character. So sp hybridized, then sp2 hybridized, then sp3. But if you look at the reactivity order for oxidative addition of a CH bond into a low valent metal center, it's the exact opposite. So what is the crux of it? Well, sterics play a really huge dominant role here. And so the steric accessibility of this sigma star antibonding orbital that you need to populate is really of critical importance. And you can imagine if you just think about a CH bond of like iso, what would it be? Isobutane, some tertiary CH bond, and you think about the sigma star antibonding orbital that needs to be populated for that oxidative addition, you can quickly get an appreciation for how hindered and how strained that reaction trajectory starts to become. So sterics play a really critical role here. And so some of the intuition that you might have just from a bond strength argument is not enough in thinking about reactivity trends here. That's the point that I want to make. Usually the reactions follow, this elementary step follows second order kinetics. Why? Because formation of the initial sigma complex is the rate determining step. And then the subsequent actual oxidative addition part of this oxidative addition is fast. As you can appreciate in this transition state, we do not accumulate charge. And so in general, these reactions are insensitive to solvent dielectric constant. And that can be used as a mechanistic tool to disambiguate between this versus the SN2 pathway. And we saw from an orbital diagram perspective, you have these notes above. So I just copied them here to get a sense for how, again, how oxidative addition is an extreme of pi back bonding. Okay, let's consider now the nucleophilic SN2 type. So if we, let me see, I'll go up here and just add some arrow pushing. Let me, and then that will allow me to draw this distinction here. And then so now we can encounter now we can consider the mechanism that's common for polar substrates where you have a good leaving group. And this is very reminiscent now to SN2 reaction. When you have a carbogenic substituent that is stereo defined, you will see stereo inversion. The A and B groups will often add trans with respect to one another. And so that can be a good mechanistic readout in terms of the underlying mechanism. In this case, during the transition state, you see that you start accumulating charge. And so because the transition state is charged, it becomes sensitive to solvent dielectric constant. We can consider a case of oxidative addition of a representative series of nickel zero complexes to get a sense for how ligands can influence the relative rates. And so if we just, in this case, consider, let's say methyl iodide, for example, then the relative rates will be as such. The most reactive form will be the nickel that's ligated with these trialkyl phosphines. Those are the strongest sigma donating. So you have really pronounced homolobe on the nickel center. It will not react, of course, through this tetracoordinate state. It will need to dissociate ligands and then react, but nevertheless, this is the most reactive. Then next up is the tetrakis triaryl nickel zero. Now, if you start pulling electron density off of the nickel through alkene ligands that are capable of pi back bonding, this will attenuate rate. And then if you go all the way to so-called naked nickel zero, only with olefin ligands that are have pi accepting character, then this is the slowest reacting. Unsurprisingly, given its close connection to SN2 reaction, better leaving groups accelerate this reaction, and keep your eye on this tosylate example. This will become important when we talk about radical mechanisms. We talked about how steric effects and polyrepulsion is important in a concerted pathway. It's also important in this pathway. And so the least, if we have a common set of leaving groups, the least hindered carbogenic substituent reacts first in the order of methyl to primary alkyl to secondary alkyl. And then tertiary alkyls generally will not react via this pathway. And secondary even is a stretch. Okay, let's consider a case study here, and we'll get some class participation. All right, Jakai. This case study will help us get a sense for the different similarities and differences between a nucleophilic versus a concerted pathway. So first, let's consider this iridium carbonyl complex. Do you know the name of this complex by chance?
Oh, sorry.
Anyone want Alex?
Vasquez?
Vasquez complex, very good. Initially reported by Lori Vasca in this report from the 60s. This is an interesting case study because Vasca's complex itself is not particularly useful in catalysis. It's not like Wilkinson's catalyst, Crabtree's catalyst, but it has great historical importance in the field of organometallic chemistry because it possesses this built-in CO ligand, which can be a beacon via IR. Remember, this is the 60s. So IR is the powerful technique for monitoring coordination environment around the metal. It has this CO ligand that's a beacon for what's happening in terms of the electronic environment on the metal. Okay, back to Jakai. So first, give me the electron count for Vasquez complex. Iridium, what oxidation state?
Should be 1.
Iridium +1, D,
8.
iridium 0 is D9 metal, so iridium 1 would be D8. And then you have 4 L-type ligands, which will give you 12 electrons. Sorry, yeah, you, I don't know why I did that, 8 electrons. And then if you add them together, you have 16 electrons. Great. Okay, let's walk this top path now. We're going to coordinate H2. It's good here. We're a square planar D8 metal, so we have an open coordination site. H2 is going to coordinate That process is slow, and then what will happen next, Jakai?
I think, to hydrogen will add like chlorine with, uridium.
Okay, and do you like adding those cis or trans?
I think this,
Cis, why cis?
because it's like a concert mechanism.
Brilliant. So Jakai is saying, based on what we just covered, H2 is nonpolar reactant. We're going to be in the concerted mechanism, and that will be cis. Okay, let's do a quick electron count for this one now, Jakai. What's the oxidation state of iridium now?
Now it's 3,
Iridium 3+, so D,
6.
D6.
And coordination number is 6, so it's 12 electron.
The total is what?
Total is 80.
18 electrons. Okay, so we've got a real world case study now to talk through those general features we described before. Let's compare and contrast. What happened to the oxidation state? It increased by 2. That's good since it's called oxidative addition. What happened to the d electron count? It went down 2. Just like we said it would. We went from 16 electron complex to 18 electron complex, coordination number 4 to coordination number 6. And this also, I think, shows this intimate relationship between square planar D8 metals and octahedral D6 metals. All right, going to stay with you, Jakai. Now we've got methyl iodide. So we're now in a different substrate category. So what might happen mechanistically?
I think this has to close the paraffilic.
Okay, so you want to do the nucleophilic mechanism. So you're going to draw this intermediate. Is that right?
Yeah.
And then
Um,
where does iodide come? Cis, trans,
trans.
trans, okay? We saw that general trend that these like to add trans. That's what we're doing here. Good. And then what about the electron count?
Still iridium 3 and
Everything's the same, right? Everything as above. Okay. Great. Questions on that? Good to just do one together so we can see those, how those general principles manifest in a specific case. Okay, now we've got radical. And radical is, I think, it has always, there's always been an appreciation for radical pathways all the way back to Kochi's work, especially ignited interest in the field. But now in the year 2025, this has become even more important, even more common. And so let's consider the two limiting scenarios of non-chain versus chain. So in a non-chain pathway first, you have an electron flowing off the metal center. And so now we're going to use these fishhook arrows, forming a new covalent bond with the halide first to generate a carbon-centered radical. That carbon-centered radical is then going to recombine with the open shell metal center. And so the metal is adjusting oxidation states here, one electron at a time, first to the N+1, then to the N+2. That's the non-chain pathway. And then the chain pathway is carbogenic radical engages with metal that generates the unpaired spin on the metal that is going to engage with the halogen atom to generate said carbogenic radical that then will eventually go on to a second metal center or a third, and so on and so forth. These radical pathways can take place for either polar or nonpolar category. If I had to say, I would say it's maybe the more common for the polar, particularly organohalides or their functional equivalents. One of the diagnostic features now is that in terms of a carbogenic substituent, if you go in stereochemically defined, you will ablate this stereochemistry because of the rapid rate of conversion of the corresponding radicals. Reactivity trends are clearly distinct from what we saw in the nucleophilic case because they track with the carbogenic, they track with the ability of the corresponding group to stabilize radicals. So here, tertiary alkyl radicals we know are more favorable or more stable compared to secondary, compared to primary, compared to methyl. And then let's look at the reactivity trends in terms of leaving group. We see some similarities to what we saw above, but look at the tosyl. I told you to track the tosyl. Now the tosyl, because it is not comparatively unreactive in radical pathways, is one of the least reactive leaving groups here. So this can be a really nice diagnostic feature of whether you're in the radical regime or you're in the SN2. A common theme in radical-based cross-couplings that you might have seen in the modern literature is that they commonly employ first-row metals, nickel, cobalt, iron. And one of the reasons is because first-row metals play most nicely with radicals. They have the lowest splitting energies. They can best accommodate, they have the lowest energetic penalty for accommodating unpaired spin in their frontier orbitals. But it's not a given that only first-row metals are capable of engaging in radical pathways, so we can consider this case of a non-chain radical radical case of platinum, third row metal here. And I'll give this for you to think about in terms of how you, based on radical pathway, how you would order this series of electrophiles in this oxidative addition. One step I just want to touch on briefly, it doesn't really fit in nicely anywhere, but I think kind of most connected to oxidative addition is called oxidative cyclometallation. And I've heard this before described as trading pi bonds for sigma bonds. So this is common if you think about reactions, catalytic reactions you might be familiar with, like the Towson-Kahn reaction. We talked about alkyne trimerization. These rely on coordination of two pi systems. And then effectively, if you want to push arrows, you're pushing electrons like this. This will form 3 new sigma bonds at the cost of 2 pi bonds. And then this intermediate has 2 carbon metal bonds that are reactive sites. And so then in the context of a Towson-Kahn reaction, you know that you have an alkene and alkyne that generates a 5-membered intermediate like this that's then reacted with CO. And again, the common thing here, the common feature that's shared with classical oxidative addition is the increase in oxidation state from N to N+2. Okay, we can, I think in the interest of time, I'll ask you all to think about problem of the day number 2 from the day 5 handout. Take 5 minutes as homework to think about it, and then when we start class on Thursday, we'll just rapid fire, get right into this as our springboard for closing out the elementary steps discussion. So if you're following along the syllabus, next class period, we'll close out discussion of elementary steps and cover metallocarbines. And then we'll be off to the races with stitching these steps together in the context of